Hello and welcome back to Calculus 1, section 5.3 on fundamental theorem of calculus. Very important stuff, as we are going to tie the entire semester together, put all of the calculus on a pile, and see how it all works together. We already know that calculus consists of limits, derivatives, and integrals. Now, limits compute y value in their nice, unique way. Derivatives measure change. And integrals, they measure accumulation, right? Because it's a sum. So, I don't know if I want to say, let's go with the area under curve, realizing that there is more than that, but we haven't gotten there yet, actually. So, yeah. Now, we also know that limits are used in some definitions of these concepts. So your f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And in the last lecture, we saw that the integral of f of x dx was given as the limit n goes to infinity, and this is where accumulation, right, comes from, because you have this summation of infinitely many of these. So these were your basic ideas. The rest of the course are details. Probably the biggest detail of all of them is the tangent line for Calc 1. And definitely for your survival in Calculus 2 would be the chain rule and sections 4, 9, 5, 2, 5, 5 for integration, and so on. Now we will be talking about setting up Calc 2 after Thanksgiving, so those of you who need to go into Calc 2, or you think you don't need to go to Calc 2 while you're at RV, but then you see that your transferring institution will require Calc 2, you definitely want to do it at our place. So probably more people than they think will go into Calc 2 eventually, either here or when you transfer out, doesn't matter. Now, what is the fundamental theorem of calculus? Fundamental theorem of calculus is going to connect these in a very interesting way. What we have is the fundamental theorem of calculus has two parts. Part 1 is going to be the definite integral. You already know that one. So you find any antiderivative and you compute that between a and b, you get f of b minus f of a. Now the part 2 is the one that we really focus on, and this one says the derivative in respect to x of the integral a to x of f of t dt is equal to f of x. So that's the big one. Part 2 is the one that indirectly gives us all of the scientific advancement which we have today. So now, what is all of this? Well, first of all, the part 1 we don't need to discuss. We spent about, 30 minutes reviewing this before we started this lecture. And we learned that last time. We know that we can also do the Riemann sum. So I would say we're pretty much set, right? We know what is going on for this particular part 1. And we also seen that area under the curve, which we are actually going to explore more later on in this section. It's the part 2 that we need to focus on. Can anyone give a glimpse of what this might mean? Like, what does it essentially say, right? Knowing that the big F and small f are not the same thing, and so and so. How can we have lowercase f and uppercase f above there with the integration, but the one on the bottom it just has 2 lowercase f's? Just take a wild guess and let's see where it leads.
Is because the derivative of x is on the outside of the integral, like it's no longer using b, it's using x as part of the integral.
So x is well, this is the derivative of x. I mean, I could have put this like this as well, right? So you will differentiate this entire integral. Like if you think of this as a 2-step problem, you integrate whatever you see and then you differentiate, right? Because that's the order of operations. If you are starting at this f of t, you will first integrate, and then when you get that answer, then you will differentiate the whole thing. So now what is happening here? Does anyone see? Look at the functions, guys. This one and this one. What can you say about it? I'm not sure if you are shy or you really can't recognize when you see 2 same things. Which would be a problem, right? It's like a set of identical twins over here. They just have a different name, right? It's the same function, which means that integrals and derivatives cancel each other out. And that is the biggest takeout from what we are learning today. So if you take this calculation and you carry it out, which is technically the proof for this, you will have, when you integrate this f of t dt, you will get capital F of t computed from a to x. And now, when you plug in your limits, the way you're supposed to plug limits, you plug the upper limit first, then you plug in the lower limit, which is a. You have the derivative of, I don't know why I'm writing it again, but whatever. you just get lowercase f of x minus 0, which is just f of x. So that means that whatever function you started off in here, you end up with the same function at the end. Now, one is in terms of t, other one is in terms of x. That's just different. We call the f of t dummy variable, but the function is absolutely the same. And it really doesn't matter what you pick. Any function, right, that you can integrate would do this. So if you start with the derivative of, let's say, 3 to x of, let's say, cosine 4x dx. Sorry, t dt. Oh, we didn't do the 4s yet. So cosine t dt. Yeah, we didn't do the stuff with a. That's later. So now your integral of cosine is sine, positive sine, computed from 3 to x. That is the derivative of sine x minus sine 3. Now, I don't care what value sine 3 is. I just know it's a number, so when I differentiate it, it's gone. So the derivative of sine is cosine x minus 0, which is just cosine x. And you can see it now. You started with this cosine t, and you ended up with cosine x, which is the same function. It's just a different variable because we had to use the dummy variable because this x is in the limit of the integral. Fundamental theorem of calculus tells us that derivatives and integrals cancel. They undo each other. They're opposites of each other, which we kind of knew from 4.9 anyway, because I started with, remember, the derivative of x squared is equal to 2x, which means that the integral of 2x dx is equal to x squared, and then we said plus c, right? Well, now you are battling this plus c simply by having these values in the integral, right? But we needed plus c in 4.9. So we know from 4.9 that integrals and derivatives are opposite of each other. We also know that if you want to check your integration, all you need to do is to differentiate. And if you get the original problem right back, then it means that your integration went well. So all of those things click in now, and we say they are all in this fundamental theorem of calculus. We have the part which tells us how to compute the definite integral, and then the definite integral wrapped inside, right, packed inside the derivative, shows us that derivative and integrals roughly cancel, right? And you get your original function back. You just change the variable, but that's still the same function. Now, implications of that are huge, because now we know that we can solve differential equations, equations which contain derivatives. Now, you will have a preview of differential equations, just a couple of sections, 2-3 sections in Calc 2, just to get some vague idea on what differential equations are. There are courses upon courses upon courses on differential equations later on. And again, those of you, right, engineering, math, physics majors, right, you will be taking differential equations. Computer science, please. Your courses are linear algebra and discrete math. There is no reason to waste your time with Calc 3 and DiffyQ because they are like 95% useless to you. So computer science majors, right after Calc 2, your job is to take both of those courses, discrete math and linear algebra. And when you say, but no, I just need to take one of those, no, you need both of those, because one is teaching you, I understand that the program says one, you can take the other as a free elective, the discrete math will teach you algorithms, and linear algebra will teach you that higher end mathematics that you need for encryption, you need it for image compression, data compression, develop, let's say, MP3 and video compression for files, and file compression in general, and just linear algebra is everywhere. And you think about it, you learn logic and basic algorithms from discrete math. That's going to be your low-end programming, like vending machines and stuff like that. And then you're going to go into huge data sets and stuff that, let's say, Google and Microsoft need you to code. In that case, right, you need linear algebra. And you'll need more linear algebra courses down the line. I mean, the introductory one is not going to cut it. But, when you're talking about your arrays, that's your matrix in linear algebra. Anyway, so now going back to our fundamental trinomial calculus here, this fundamental trinomial calculus gives rise to your ability to solve differential equations, and differential equations are the base of everything STEM we ever made, because all of your physics formulas and everything else is born from physics are differential equations. You observe some feature of nature, let's say that the temperature of the, you take turkey out of the oven, and the way at which the turkey would cool is with the room temperature the turkey is in. Clearly, it's not going to cool down if you leave it in the oven, right? Even you turn the oven off, but it still remains really hot for a long time. So that means that your turkey will not be cooling down. If you take it from oven that is, let's say, 400 degrees, and you put it on a countertop, well, now the turkey is in the room that it's 70 degrees, let's say, and it's going to start cooling off. Now you can say that the change in temperature, right, of the turkey is proportional to the difference between the turkey's temperature and the room temperature, which makes sense to observe. And when you observe that, you make a differential equation. Now, you heard me say change, right? Change in temperature of the turkey. It's going down, right, because it's cooling off. So that's a change in temperature. And because it is cooling down, the temperature change, that's the derivative. So you have the derivative. Now, to solve that, you will actually have to use integration. And this is where this thing kicks in, fundamental trinomial calculus, because it says that the derivative can be undone by integration, which means that we can solve that differential equation and learn and understand the formula about cooling and heating objects as well, which is called Newton's law of cooling. And you will have the preview of that, obviously, in Calc 2. But now, what's important for you is to understand that derivatives and integrals are opposites of each other, and that's captured in that formula as well. Now, we can also go back, and I'm just hoping that you're going to do better on this than looking at these two things. We can also take a look at their formulas through limits, and you can tell me why these two formulas are opposites also, like why would they cancel each other. So if I write the formula for the derivative, write formula for definite integral here using, again, limit n goes to infinity, summation I goes from 1 to n of f of xi times delta x. So can you guys make comments on this and tell me why would derivatives and integrals cancel each other looking at the definitions that they have?
One's multiplication and one's division.
Beautiful.
One goes to 0 and the other goes to infinity.
Excellent. This one and this one. And there is one more. Let's see if you can guys find one more major. So division and multiplication are opposites of each other. Excellent. We also have 0 and infinity. What else?
Subtraction, addition.
Perfect. There you go. So those are your opposite pairs. Okay? Those are your opposite pairs. And you can see that these two formulas are completely opposite from one another in every aspect of their existence, right? Which means that they should undo each other, and they do, right? So that's why we can say that the derivative of x squared is 2x and integral of 2x is x squared plus c. But yeah. Okay, the last part that it's left for us to discuss here is that part 1, where we say value of definite integral versus area. So value of definite integral versus area. So what we have discovered in our first lecture, and I was very careful to ask just particular type of question, is we learned that if you have some kind of function between a and b, right, that's f, function f of x, you can find the area of the shaded region by simply running the integral like this, which eventually gives you a number, right? Okay, that's something that we can easily verify. You know, this is not a proof, but we can verify with the example. Let's say you want to compute area of a triangle. Which is 1, 2, 3, 1, 2, 3, 4, 5, 6. Now, you know what the answer to this is, right? It's 1/2 of the base times the height, which is 9 units squared. So you can go into this picture and count, physically count 9 squares. 1, 2, 3, 4, 5. This should go through here, so 6. And then that's 6. And then the rest over here would, right, this would jump over there, create 1. This piece would jump over here, would create 1. And this piece would jump over here, would create 1. And there is your other 3. So you are creating 9 of these squares. And this is 9 units squared. Actually, now that I accidentally erased that line, maybe I can, since I'm zoomed in, do a better job, because it has to go through these points. So let's see, it goes there, goes through here, goes forever this way, goes forever that way. There we go. So now you see that this portion over here fits up there, and it creates this as a one big square unit, right? And we are getting rid of that part there. So you can quickly see that this is actually 9 because you can count them. That's great. And then we learned that we can also use integrals. So if we go and here say, oh, this is y equals, we go 3 units down, 6 units over, and then plus 3 on the y-intercept. This turns out into the function f of x as negative x over 2 plus 3. That's a function, right? When you simplify this linear line, and y is f of x. So now your area calculated by the integral is going to be area under the rectangle. I'm sorry, under the area of the triangle, area of the triangle, and you start at 0 and you end at 6. Those are your A and B values, because 0 is the most left you are, and 6 is the most right you are for this triangle. And then you have your function, which is negative x over 2 plus 3. Have to put that in parentheses because all of that is times dx. And now you just forget about geometry, forget about everything. You just do the calculation way you are used to. So it's going to be negative 1/2 is a constant you copy. Then you get your x squared over 2 integral of x plus 3x computed from 0 to 6. Now this is going to be negative 1/4 times 6 squared plus 3 times 6, and then minus negative 1/4 0 squared plus 3 times 0. Now you see that you get a big fat 0 right from here. That's all zeros. So all I have is negative 36 over 4 plus 18. That's negative 9 plus 18, which is 9, which is what we expected. So we can calculate the area under the curve very easily, right, if we are able to integrate the function. Now we're going to compute the area under sine x dx from 0 to 2 pi. And we want the area. Actually, let me move this so I can put the area. There we go. Put it right here. There we go. And say area. Let's go area under f of x equals sine x on 0 to 2 pi. Now you know what to set up. This is standard. As soon as you're looking for area under the curve, you immediately take the definite integral of the function between the two values you had for as your limits, right, or integration. So now when you do this, you go and just compute very quickly, and you see that something is wrong, right? Negative cosine 2 pi minus negative cosine of 0. Well, if you draw your cosine graph, you see that at 0, cosine is 1, and also at 2 pi, cosine is also 1. So you get negative 1 minus negative 1, which is negative 1 plus 1, and you get a big fat 0. And you go, huh? What? 0? No. Hell no. No way. No way. Because when I draw a sine function from 0 to 2 pi, there is definitely area that I can color in. There is definitely area where I can color. So I don't care what the integral tells me, that's wrong, right? Because there is... Now, did we do the integral wrong? No, everything is correct. And yes, the answer is 0. But there is a big, big, big asterisk next to what you guys learned the last class and what we are learning now. And that is that if the function at any point dips below x-axis, you create negative area which will be subtracted. Now, in this case, sine function is symmetric on origin, meaning that the bump under the line, under the x-axis, and the bump above x-axis are identical, and they cancel perfectly down to 0. So you technically found a net area, right? But you want to say, what is the area that I can color? And that area, well, we have to use some rules and things for integrals to actually see the proper way to compute this. So this is not area, so I'm gonna put the little, I kind of want to, it's not wrong, it's just, let's try it this way, not what I was looking for. How about that? Not what I was looking for. So how do we fix this issue? You fix this issue by use of the rule which states, right, from last class, rule that states that any integral can be interrupted anywhere as long as you add the two integrals together at the end. So if you take a look at this formula from last time and the picture that is associated with it of some function f of x, this is your a, let's say this is your c, and let's say this is your b. They don't have to be equally distant, none of that stuff. So if you take a look, this is going to be your, let's use different color, this is going to be your integral 1, which covers this area, and this is integral 2, which covers that area. And you can see that the first integral is a to c, and the second integral is c to b, right? So we have all of that on display. So now that means that when I draw my sine function, I see that there is a piece that it's under the x-axis, which means that I need to bring that one up above x-axis, which means we need to stuff it into absolute value. So, looking at my sine graph, this is a terrible sine graph, somewhat better. So looking at my sine graph, when I have my 0 to 2 pi sine x dx, and I know that if I do everything in one shot, it will give me 0, which is not something I want. I need to look at this and say, all right, the switch happens here at pi, so pi to 2 pi is, in quotation marks, bad region. So I'm going to break my integral 0 to pi of sine x dx and leave that one alone because everything is cool, right? It's above x-axis and all of that stuff. The noisemaker is the second one, the integral pi to 2 pi of sine x dx, because that's the one that is below x-axis. And the way to fix that is to put these absolute values. Now what absolute values do is they bump this on top like this. So now when you add your two areas, you will have the actual area that you are about to color. So we start by, over here, the calculation. Start the same way as before. We integrate sine, that gives us cosine x from 0 to pi. And then we have plus absolute value, another cosine x, but this one is from pi to 2 pi. So all I need to do now is to plug all of these values in, and I'm done. So we have cosine of pi minus cosine of 0 plus, in absolute values, we have cosine of 2 pi minus cosine of pi.
I may be wrong here, but shouldn't that be negative cosine?
No. Derivative of Wait. Yes. Yes, 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 yes. Negative cosine. So that's a plus, that's a minus, that's a... There we go. Yes, 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 yes. Integral of sine is negative cosine. Earlier today I gloated in the fact that hyperbolic sine and hyperbolic cosine don't have to worry about these changes in signs, and now there you go. I got the reminder of the cosine. Anyway, thank you for that, because obviously that would make everything wrong. So now we have a negative cosine of pi. Oops. How much is cosine of pi? Well, as always, the best way to deal with these values is to just draw the function. There's your pi, there's your 0, there's your 2 pi. So when you look at this, pi, cosine of pi is negative 1. That's the y value. So we have negative 1. Plus cosine of 0 is 1. Plus absolute value. And over here you have cosine of 2 pi is 1, so that's negative 1 there. And cosine of pi is negative 1. And when you compute this, you get 1 plus 1 plus absolute value of negative 2, which is 2 plus 2, which is 4, and you move on with your life. It's really awesome to see that area under sine or cosine graph for this one principal period is exactly 4. I know pi is no irrational numbers. It's just 4, which is really funny. I don't know. It's funny to me. Maybe not funny to you, but definitely funny to me. So now we have to be careful when we are dealing with problems which want the dealing with problems, right, with a dip where the function dips below x-axis. So area equals integral a to b f of x dx only when f of x is equal to 0 or larger than that. Otherwise, nope. Otherwise, you're dealing with the net area, which is the negative area, which you have to subtract. And you'll have a couple of homework exercises, so try it, and then you can bring it, next time we get together. That's Monday. Next week, you can bring your questions. We can discuss those things. That's fundamental theorem of calculus. I hope you're not disappointed. The next lesson is also introducing some of the formulas. So we'll get there after the break. Bye.